Hello. In this first lecture really devoted to dimension reduction methods, we'll cover principal component analysis, probably one of the most common methods in the toolbox of machine learning and multivariate data analysis. I'll start with outlining some mathematical detail, then go over a more detailed interpretation, and then finally contribute something that is a little bit different from the usual treatment, namely making the PCA spatial, or taking a spatial perspective towards the principal components. And from now on, the materials that I cover in these slides are described in quite a bit of detail in the matching workbook chapters. So I refer you to those chapters for specific technical details and especially references as well. So, principal component analysis, the idea I already outlined earlier is to replace the original variables, let's say there's P of them, by a smaller number of principal components. And the principal components are not very useful if they don't result in considerable dimension reduction. So if you have 10 original variables and you end up with 10 principal components, that doesn't really help you. So what you want is to have a situation where you can reduce the dimensionality significantly so that K is much smaller than P. And the other aspect that you want, which I mentioned in the other lecture, is that you want to capture as much of the information content that is available in the P variables, in the larger number of variables, in the reduced number of components. So principal component analysis is one particular way to achieve this. It has a particular objective function, namely to maximize the explained variance. And you can come up with other methods that use different criteria, but this one is by far the most commonly used. And as is often the case, it's been reinvented a number of different times, and it's known under different terms in different literatures. For example, in the machine learning and operations research literature, it's known as the Karhunen-Loewe transform. In image analysis, remote sensing, it's known as empirical orthogonal functions. And so there's different terms for these things, but they're always the same mathematical result. So what we want to do, what our objective function is to capture the variance, or you can think of it as the information content, the variance covariance matrix X prime X. If X is our n rows P columns, the P columns are the different variables, we want to capture that variance as closely as possible by these K principal components. So the three results that we get by solving this problem, I won't do this in mathematical detail here, you can find this in a range of different textbooks, but the idea is, first of all, you want to capture as much of the variance as possible. Secondly, you make the principal components orthogonal, which means they're not correlated, and also that they're standardized. So they're standardized so that the sum of squares, so to speak, is 1. And you obtain this by scaling the coefficients, because in essence, a principal component is a weighted sum of the original variables, and the weights are these coefficients. We call them the loadings, and we want them scaled so that the sum of their squares sums to 1. So formally, what we're doing is x1 through p are the original variables, a, i1, ai2, aip are the loadings, and we multiply the original variable by the loadings to get an observation of the new principal component. And each principal component can be written this way. It's a weighted sum of the original variables. Now, for all practical purposes, in order to avoid issues with different variability in the original variables, they tend to be standardized so that their mean is 0 and their variance is 1. That's a pretty common procedure. The components themselves are orthogonal, so another word for uncorrelated. So if you multiply two different components with each other, it's 0. And then, as I mentioned, the coefficients are scaled so that the squares sum to 1. And so you can think of this as an optimization problem. How do we find these A's such that the resulting C's maximize the amount of explained variance? And in multidimensional space, and I'll show you in a second for 2 dimensions, but imagine for 2 dimensions this is irrelevant. What we're really working with is high dimensions, where P is 10 or hundreds or sometimes thousands of variables. And so we're in hyperspace, and we try to fit a linear hyperplane, if you wish, to the point cloud in hyperspace. It's easy to visualize this in 2 dimensions, but as I said, that's not really necessary in 2 dimensions. But let's say we have 2 variables. This is the point cloud in 2 dimensions. So rather than going vertical, horizontal, we fit the line so that it explains the maximum variance, so in the direction of the largest variability. So you see the point cloud is elongated in this direction, which means the variation is the largest in that direction. And then, as we just posited, the components are orthogonal to each other, so we know this one has to be perpendicular to the first one in the second direction, which is obviously, if there's only 2 directions, then whichever is not the one with the largest variance is going to be with the smallest variance. But this illustrates maybe what is going on. So we're trying to find the coefficients of this line so that we can express this line as a function of x1 and x2. That's really what we're trying to do. And as it turns out, our friend, the eigenvector, comes in very handy. And as it turns out, and I'm sparing you the mathematical detail, but it's a simple optimization problem, each principal component can be expressed as the product of the original matrix with an eigenvector, one of the eigenvectors. So the original matrix, as I mentioned, has n rows, the number of observations, p columns, the number of variables. The eigenvector has p rows, one for each variable, so to speak, because the eigenvector is the eigenvector of the variance-covariance matrix x prime x. Recall in the previous lecture that we did the spectral decomposition of x prime x, or we did the singular value decomposition of x, and both of those gave us the eigenvectors. So in principle, we have as many eigenvectors as the dimension of x prime x, which is p times p. So we have p eigenvectors, but that defeats the purpose, because the whole point is to do dimension reduction. So the way we approach this is we pick the eigenvectors associated with the largest eigenvalues. So for each eigenvector, there's an eigenvalue. We sort them basically in order of declining eigenvalues, and we pick a few of them with the largest eigenvalues. As it turns out, the eigenvalue corresponds with the explained variance. So we're trying to explain as much of the variance as possible, so we're going to take the eigenvector with the largest eigenvalue first. We multiply each of the original variables, which is a column in x, with the corresponding value in the eigenvector, and that gives us this new variable, so to speak, the principal component, C, as the weighted average of the original variables weighted by the element of the eigenvector. So as I previously mentioned, we call this the loading. So the loading of a principal component is what you multiply the original variable with. And as it turns out, the loading is the matching value in the eigenvector. Now, one thing to keep in mind, and this can be very confusing in the beginning, is that the signs of eigenvectors are arbitrary. So an eigenvector that you get from a procedure, either say spectral decomposition, which you do numerically, there's no analytical solution, or single value decomposition, which again is a numerical operation, there's no analytical solution. These eigenvectors may not be the same. However, the sum of the squares are the same. The sum of the squares sum to 1, but since they're squares, some of them can be negative or positive. So this is something that if you're not aware of this, it can be very perturbing, because depending on the software that you use, a different convention may be used. For example, in the example that I'll be using in a few minutes, the results using a strict eigenvalue decomposition, like say in eigen in R, have the opposite sign from a singular value decomposition, which is the one we use as the default in GeoDa. So unless you know that, you could be very wrong in interpreting the results, because there's no such thing as an unambiguous high and low. It all depends on the signs, and the signs can be flipped around. So be aware of which method is used when you're using a particular software package, because you could end up with the opposite signs. But so our problem is really solved, because as it turns out, this very complicated problem of trying to find these coefficients, the loadings, so that the new principal components maximize the explained variance, is solved very easily by finding the eigenvectors for the variance-covariance matrix X prime X. And remember, the variables are all standardized, so that the diagonal of this X prime X matrix is 1, is always 1, because the variance is equal to 1. The off-diagonals are not, but the diagonals are 1. Okay, so we now have all the pieces. We have the covariance matrix, we get the eigenvector. What do we do with this stuff? What is the typical result of interest? So first of all, we want to see the loadings for each principal component. In other words, how do the original variables contribute to the computation of the principal component? And those are nothing but the elements of the eigenvector that corresponds with that component. Then the second piece of interest is the new variable, the principal component. So for each observation for this new variable, this principal component, we get a score, and those are the new observations those are the observations on the new variable, and these are nothing but the actual product of the original data matrix with the matching principal component. And then finally, we're interested in finding out how well we do. And remember, the objective was explaining the variance, explaining the information contained in the variance-covariance matrix, and trying to capture that as much as possible. So we're interested in the proportion of the overall variance that is explained by our principal components, and that, as I mentioned, is directly related to the eigenvalues themselves. Okay, So let me give a little example, and this example will come back over and over again in the material that we cover from now on. It's actually a classic data set for the moral statistics in France in 1833. It's a data set developed by a French sociologist, André Michel Guéry, and it has social indicators, historical, from 1833 for 86 French departments. And it was one of the first multivariate statistical analyses that also used geographic visualization. And the data is a sample data set in GeoDa. It's also available as an R package, and it's been analyzed and reanalyzed a number of times as a classic example of illustrating geographical analysis with multivariate data. The 6 variables that we use are crime against persons, crime against property, literacy, donations, births out of wedlock, and suicides. And Guéry used a weird convention. So typically, when we talk about crime, we use a crime rate, which is the number of crimes over the population. Guéry flips it around. It's the population per crime. So whereas a crime rate, a good crime rate is a low crime rate, if you flip it around, then you want a high pseudo-crime rate. So all these variables have been flipped around, so to speak, so that larger values means better conditions. So larger crime against property actually means less crime. So it takes a little bit to think about that, but once you know it, it's straightforward. This is a very challenging data set. As you can see from just a glance at these different maps, there's not that much correspondence in the map in the sense that you would see all the blues in the same position. For example, we see blue here and blue here, but then this is not that much blue and this is a lot of brown. And then same here, we have a big blue in the top, but then this is brown, this is blue again, but then this is brown again. So this is one of the challenges associated with dealing with multivariate analysis as opposed to univariate analysis, where we only have to worry about one variable and one map, so to speak. We can also look at the correlations between the 6 variables, and these correlations range from being pretty decent, like this is the Moran's eye, pretty decent, like 0.5 between suicides and crime against property, but some of these are also pretty dismal, like crime against persons and literacy, or the births out of wedlock, and crime against persons. So this is actually a very challenging data set to carry out principal component analysis, because the whole point of principal component analysis is to try to capture, if you wish, the correlation structure among these variables by a linear combination of a very small number of linear combinations of the original variables. And that's going to be a challenge for this data set. And just to compare here, Moran's eye, without giving you any significance, they're all highly significant, but they do rate in order of magnitude from about 0.2 to 0.7. So literacy is the most strongly correlated, spatially correlated variable. Since we're using the same weight matrix, we can actually say something about the relative magnitude of Moran's eye. Typically, as you may recall from the intro class, you need to use the z-values to make such statements. Okay, so we have our 6 variables, we have them standardized, and then this is the kind of result that GeoDa, for example, gives you for the principal component analysis. So let's look at this for a second, and then I'll review it in more detail. So first of all, it tells you the method that is used, which is in essence the method that we use to find the eigenvector. So the default in GeoDa is singular value decomposition. Then we have the standard deviation, which is the square root of the eigenvalues, as we'll see in a second. The proportion of variance from the first eigenvector, from the second eigenvector, third eigenvector, and here the cumulative proportion of the variance. So by the time we have 3 eigenvectors, or if you wish, 3 principal components, we explain 74% of the original variance. The Kaiser criterion and the 95% threshold criterion give us a guidance into how many principal components we should actually use. In particular, the 95 percentile criterion doesn't do us very much good, because going from 6 original variables to 5 principal components is not much of a dimension reduction. So that's what I meant when I said this is actually a challenging data set. So these are the eigenvalues, and then the eigenvectors are here. So for the first principal component, these are the values for the first eigenvector associated with the first eigenvalue. And we multiply the standardized values of the original variable by this coefficient, and then add it all up to get the score for the first principal component. And then finally, in this last table, we see the squared correlation between the original variable and the principal component, which shows us 2 things. One is, how is the variance in the original variable spread out over the different components? For example, here we see that almost half of the original variance is captured by the third principal component. And also the vertical view shows us which variables are most correlated with this principal component. And for example, here we see that crimes against property, literacy, infants, and suicides are pretty highly loaded, but crimes against persons are not, and neither are donations. These are squared, so there are no signs. Here the signs depend on the method that is used. And recall that it's arbitrary, so the minuses could become pluses and vice versa. So now let's take a closer look. This is the first set of results, and they are all derived from the eigenvalues. So these are the eigenvalues of the X prime X matrix, the variance covariance matrix. Each of the eigenvalues gives the actual variance associated with that principal component. The sum of the eigenvalues is the total variance in the system. Now think for a second what this total variance would be. Recall that the variables are all standardized, so they all have variance of 1. So if we have 6 variables, then the total variance in the system is 6. And in fact, except for rounding, this is 6. So the sum of all these eigenvalues, your variables are standardized, the sum of the eigenvalues will be equal to the number of variables. The standard deviation is simply the square root of the eigenvalue. So 1.46 is the square root of 2.14. Then we know the sum of all the variances is 6. The proportion of the first eigenvalue out of 6 is this fraction of the variance that is being explained. So we can compute that by hand, or of course GeoDa does it for you. We see that the first principal component explains about 36%, then it's dropped to 20%, then it drops to 18%. So it always drops because the eigenvalues have been sorted in order of magnitude. And then once we have the individual proportions of the variance, we can look at the cumulative proportions. And here we see after 3 we have 74%. After 5 we have 95%. The Kaiser criterion is based on the eigenvalues that are larger than 1. So if we look at this spot here, we see that the first 3 eigenvalues are larger than 1. That's where this number 3 comes from. The 95% threshold is where this 5 comes from. So that's actually not very good. So this snippet from the table is, as I mentioned, all derived from the eigenvalues, and they tell us something about the variance, the amount of the variance that is explained. The second aspect, before I get there, so as I mentioned here, the Kaiser criterion tells us how many principal components we should use based on the eigenvalues. The 95% threshold criterion, same thing, based on the cumulative proportions. Now, we can also visualize this, and we can go 2 routes. This is called the scree plot, and the scree plot shows the proportion variance explained by each additional principal component. So we start here, then it drops even further. This is kind of an ideal shape, and you can, this is also sometimes called an elbow plot. You can look at the elbow plot, and where you see that it flattens out, say around here maybe, or around here, then you cut off, and these are the principal components that you use. So the graph on the left is the ideal graph. That's what the textbooks show you. The graph on the right is the dirty counterpart with real data. So you see that, this would suggest a flattening out here, but it is not flattening out at all. So this is actually very difficult to interpret in terms of how many principal components we could use. So in essence, GeoDa actually doesn't provide a scree plot, but you can of course draw it readily from the information provided in the based on the proportion of the variance that is explained. So there's 2 ways of looking at this. In this particular plot, we're looking at the actual proportion explained, and in the following plot, we look at the cumulative proportion of the variance explained. And again, in the ideal case, we want to see a flattening out of this curve. In the Gary case, we don't see much of that at all, and it's very difficult to interpret. So the notion of a scree plot, either based on the variance proportion explained or on the cumulative variance proportion explained, is to find an elbow in the plot. So you see it dropping and then flattening out. In practice, it's not that easy. Okay, as I mentioned, these first set of results are all based on the eigenvalues. The next set of results are all based on the eigenvectors. And we know that the loadings, as I mentioned before, are actually the eigenvector. So we compute the observations, the scores for the new principal component by multiplying the standardized values of the original variables with the matching coefficient. And these coefficients are scaled such that the sum of their squares is 1, and you can readily verify it. So you see, for example, that the first, second, third, fifth, and sixth component load negatively on crime against persons, but the fourth one loads positively. And so, as I mentioned, the signs are arbitrary, so you have to be careful in interpreting this in an absolute sense. But you can see when they're opposite that, this is going to be the importance of low values of crime against property, which is actually high crime. That's the strange interpretation. So this is how you can intuitively interpret how the principal components are made up. But as I mentioned, this depends on this arbitrary sign. And to control for that, we take the squared correlation between the original variable and the principal component. And as I mentioned before, this shows us very nicely in the horizontal how the original variance, in this case, is essentially explained by principal component 2 and 3. And then in the vertical direction, we see that the contributors to principal component 1 are primarily crime against property, literacy, infants, and suicides. In principal component 2, it's crime against persons and donations, and the other variables like crime against property have a very low correlation, literacy as well. So these explain different dimensions of the variability in the process. There is a whole art to interpreting the principal components. In fact, there's a whole field of application called factor analysis that carries out various rotations in order to facilitate the interpretation of the principal components, or the factors as the case may be, as a function of the original variables. And so then you can give them names like social deprivation, degree of religious belief, unemployment, things like that, where a bunch of these variables group themselves into categories that you can give a name. But that's very tricky, and as I said, it's mostly an art. It's not really that scientific necessarily. Okay, then the biplot, which GeoDa does not provide, plots any two principal components against each other and shows how they load relatively on a particular variable. So what does this arrow mean? This arrow means that for the first principal component, the horizontal direction, the loading is negative because it's to the left of 0. But for the second principal component, the loading is positive because it's in the positive direction. And the same for the other variables. I find that the interpretation of the square correlations is actually more useful to understand how the principal components are made up. As I mentioned, the principal components are uncorrelated. So if you plot them in a scatter plot with the two principal components each on one axis, the regression line has a slope of 0. This is for the singular value decomposition. If you run it using the eigenvalue decomposition, so the spectral decomposition, then you get this result. Now you might say, hey, this is different. But it's exactly the same thing, but flipped. So, for example, see this area here on the right of the axis? In the previous method, these are the same points. So the points are the same, relatively speaking, but the signs are flipped for the first principal component. Okay, so far, traditional principal component analysis. This last part is a little bit different, and I would argue fairly unique to my perspective on this, and it is how to spatialize the principal components. And first of all, obviously, we can map them. So this is a map of the natural breaks map of the first principal component. Tend to have high values in the north. The second principal component tends to have high values in the south. But we have to be careful with this interpretation. As I mentioned, these are two quantile maps, and they're identical except that the categories are flipped. And they're flipped because the one on the left is based on the singular value decomposition, and the one on the right is based on the eigenvalue method. So the regions are exactly the same. So this region here of dark brown is the same as this region of light yellow, but it's a different color. So what is the top quartile here is actually the bottom quartile there. And similarly, if you do a box map and you find outliers, So this is a bottom, a lower outlier. Here, that is actually an upper outlier in the other method. So the moral of the story is, be careful when interpreting the results, especially when characterizing them as high or low, because depending on your method, the signs of the eigenvalues may be different, and that will throw everything for a loop. So you can obviously look at the groupings of the observations, and they don't change. As I mentioned, the region, say this blue region is the same as this brown region, but the order is flipped. So what is low here is high there, but the grouping is the same. So the grouping is what's important. Then pushing this even further, we can use principal components in local cluster analysis. For example, we could use a local Moran, illustrated here, significance map, or a local Geary, and we identify locations, for example, in the local Moran, high clusters, low clusters, as well as a spatial outlier. Now, what does this mean? I mean, see, the spatial outlier here is this outlier and this outlier. So the local clusters are, they do depend on the sign. So what is high here will be low in another method, in the other method, but they will be the same clusters. Why is this useful? Well, if you recall the discussion of multivariate local clustering in the intro spatial data science class, that was actually pretty challenging. That was hard to do and hard to interpret. Well, this is a way around, because the first principal component, not in this case, but sometimes we're lucky and the first principal component explains, say, 50, 60, 70% of the overall variance. So then you can argue that the first principal component is actually a pretty good representative of the variability across the multiple variables, but is simplified through the dimension reduction to a single variable. And now we're in business. Rather than having to deal with this very complex analysis of local spatial autocorrelation for multiple variables, we can carry out the usual approach for just one variable using, say, the local Moran. And then we can use our linking and brushing to assess actually what this means. So we can see by selecting the observations in the high cluster what those correspond with in terms of the magnitudes for the different variables involved in the analysis. And so in this particular case, we see that the observations in this cluster, especially for these two variables, track very closely. So this parallel coordinate plot on the right-hand side allows us to see how the observations identified as clusters, how they actually act in terms of their composition, in terms of the different variables that make up, that are analyzed and that are combined in the principal component. So this ends our tour of principal component analysis. It's all about eigenvalues, as we saw, the eigenvalues and eigenvectors. The eigenvalues give us a handle on the amount of variance that is explained, which is our objective, our goal. The eigenvectors give us the actual coefficients, the solution, so to speak, to the problem, to give us the coefficients with which we have to multiply the original variables to get the principal components. Once we have the principal components, we can analyze which variables contribute to them, we can map them, we can use them in a local spatial autocorrelation analysis. We have to be wary of the signs. They depend on the method that's used to compute the eigenvalues, but we can use especially if the first principal component explains a significant proportion of the original variance, we can use them instead of the much more complex multivariate LISA analysis. Next up is distance preserving methods, in particular multidimensional scaling. See you then.